So, hello everyone, welcome to code.talks. My name is Tadeh. I'm a senior DevOps engineer at Agile. I've been working in this area for the past 6-7 years, and I've been living in this wonderful city for the past 2 years. In my spare time, I'm a huge sports fan, whether it's watching basketball, football, or Formula One. So if you really are into those sports and are a nerd in it, definitely reach out to me. We can discuss some good stuff. About Agile, the company I work in, we are a ad tech scale-up. We have two sets of main customers, advertisers and monetizers. Advertisers are a set of applications like newbie games that they want to showcase themselves. On the other hand, monetizers are a set of well-established applications that have placements inside their applications to showcase some ads with advertisements. At Agile, what we try to do is to smartly connect these two sets of customers together via machine learning algorithms. And in the end, our goal is to show the best advertisements to the correct set of user demographics. Since last code.talks, we have grown a lot. We are now almost 2 times in our size in the team. We have now around 600 terabytes of data in our data lake, and we make around 5.5 billion API requests daily, which is huge. And with this amount of growth in data comes the responsibility. So we need to use this data for our growth to grow even more. And we do it by running, for example, business analytics pipelines, creating business analytics dashboards, running some analytics in our core engine, which is Athena, for example. And this way we make sure that we make data-driven decisions. But how many times, as a developer or like a leader, a project manager comes into your room and rages about the cost increasing because of a deployment or service uses? They're like, why this is happening? We need to decrease the cost. And that's exactly what happened to us recently. So recently we had one issue with our query engine that I already discussed, which is AWS Athena, and we saw around 500% increase in cost during the past year. And this is coming with the growth in our BIs and also data. Also, our forecast showed that this trend will continue in the upcoming months, so we needed to somehow stop this. Before understanding that, let's see how exactly we are filling our data lake, because yes, it's easy to understand we had the cost grew, but we need to understand what resources we are using for that purpose. So we have different set of data sources and databases like DynamoDB, like RDS, which is our MySQL cluster, and our microservices. All of them via different streaming services from Kinesis to Kafka, writing data to our data lake, which is an S3 bucket. And in the end, we have our schema, set of schemas in a glue table, in glue tables, and we connect these two in the end and run queries in our core engine and see the results. So we needed to rethink about what we need actually from a query engine, how we can reduce the cost, what we need actually with our current scale. So we wanted cost efficiency, we wanted compatibility with different tools, and also we wanted the efficiency and also flexibility and control over our cluster. With Athena, it was kind of a black box. So yeah, they were like charging us per terabytes of data scanned. We were vendor locked by AWS. We couldn't take over control of our cluster. So all of these created a black box for us, which we couldn't take and rethink about it. But what was exactly inside that black box is just a well fine-tuned version of open source technology called Trino. So AWS team is running a fine-tuned version of Trino cluster on the back of their services, and that's how their core engine is operating. We went and looked at the architecture of Trino. So how the architecture looks like is that it has, for example, a set of clients like JDBC clients or CLI. Users send their queries. We have a coordinator that manages those queries, send it to different set of workers. Those workers go and get data from like different object storages, which data resides there. In the end, it connects that the coordinator connects to a Hive metastore, for example, get the schema, combines the query results, and sends it back to the user. So what would happen if we have our self-managed version of Trino? What would be it comparable to the AWS Athena? So here we will just pay per provision. We won't pay per terabytes of data scan if we have our version of Trino set up. We can play with the autoscaling. We can make it more flexible. It's in the end an open source technology, which in our team we appreciated a lot. And in comparison, we will get rid of this vendor lock-in. But it comes with some cons also, which are, for example, more engineering and more overhead. But this was acceptable for our use case because with our scale, we are able to handle this amount of engineering overhead. But if you are a startup or you are just started, for example, analyzing data and you are small in company size, I would definitely recommend you to go with AWS Athena because in the end, you won't want to spend so much time on engineering parts where you want to just get the result fast and grow faster. So now that we decided to continue with the Trino on Kubernetes, let's see how this journey went. Before starting to go deeper inside Kubernetes, I just want to first introduce you to our data science environment on AWS. So we have a separate AWS account for our data science environment and jobs. As you can see here, we have a client-facing side, which is an application load balancer. Request comes from here, and all the data scientists and the BI people, for example, are using this environment via this client-facing side. Then the request goes to our computing set of instances, like EKS, which is the Kubernetes on AWS. They are backed by EC2 nodes, and an open source technology called Carpenter is managing those nodes for us. We have also our database and object storage, which is RDS and Amazon S3. We have a set of nice open source logging technologies like OpenObserve and FluentBit to ship those logs. And we have an industry standard set of tools for our monitoring, which is Grafana and Prometheus. But the heart of our data science environment is our machine learning tools. So we have a huge and a strong set of open source technologies that we use in our daily data science tasks, like Airflow, Spark Operator, Jupyter Hub, MLflow, Open Metadata, and we wanted to add Trino to this set of important tools. So as you see here, what happens after you decide to deploy some service on Kubernetes, you have two choices. Whether you go with the Helm chart or with the operator. For Trino, we did a research and we found that for Helm chart, there is an official, well-maintained Helm chart that we can use. It's simple to set up and also it's easy to configure. But for operator, there was no official operator. So we decided to skip for now. There was one operator by Stackable, which added more vendor coupling for us because they needed some components to be there as a requirement. But if you had experience with it and you think it's better, feel free to reach out. We are still open for improvements in this area. In the end, we decided to go with the Trino Helm chart. You can see it's on the Trino GitHub repository. It's easy to pull and start working with it. And when we were working with it, we already saw a huge room for improvement in some parts of the Helm chart. So we didn't stop. We did already 2 contributions on this project. Both of them are merged, so feel free to check it out. And if you want, you can scan the QR code and see what are they about. So now we have Agile Trino architecture. How it looks like is that we have the user sending the query, for example. It goes to the application load balancer. Then the load balancer sends that query to our ingress. And that ingress sends the query to our coordinator, which is a deployment with one pod. And we have a set of workers as a deployment connect to the coordinator. The workers connect to our S3 bucket, which is our data lake. And coordinator gets the schema from our glue tables. And in the end, the same architecture helps us to get the results for a query. One challenge that we had initially was that, okay, at Agile, how we set up our projects is that per project, we have a different AWS accounts to make the separation of concern. And this helps us a lot. But the problem is that we need to somehow connect from the Trino, which is in the data science account, to different projects, which each of them have their own version of data lake. How we achieved it, it was with the IAM roles, different IAM roles, and you can set them in different catalogs. So if we have, for example, project 1 and project 2 catalog in our Trino setup, you can pass an IAM role ARM, for example, for S3 and the glue parts, and you define an IAM role in each project with a set of policies that can connect to those buckets and tables. And in the end, what you need in the DS account, which is the source account of Trino, to be able to assume those roles, which is really easy. Okay, now that we had our initial cluster set up, we tried out some queries and we were so happy that, okay, we can now run all the queries that we want, but it came with a problem. Because we had a constant number of workers, like imagine 3, 4, doesn't matter, and some queries ran successfully, even faster than Athena, but the problem was that if we wanted to run like larger queries, we needed to auto-scale, and we need to set up this in a proper way. When it comes to Kubernetes, there are two ways usually to autoscale, whether you use horizontal pod autoscaler or vertical pod autoscaler. For our setup, vertical pod autoscaler wouldn't help because it would stop us from parallelizing our queries, and which that parallelizing helps us to make the queries fault tolerant. So we went with the horizontal pod autoscaler. And with horizontal pod autoscaler comes two famous triggers, whether you scale based on CPU or memory. For CPU, it was easy for us. We would just check out our cluster utilization of CPU. If it's more than 50% on average, for example, then we would scale up and it would work for us. But for memory, it doesn't work that easy. Why? Because Trino is written in Java, and the problem it has is that it doesn't release memory as soon as we want after the query finish. So this way, we will be stale for a long time, and our workers would be stale without running queries, although they are showing high memory usage. So we needed to make this memory scaled, memory-based scaling much more efficient and also much more smart. What was our solution? It was KEDA. KEDA is Kubernetes event-driven autoscaling, and how it helps us is that we have a Prometheus instance. That Prometheus instance scrapes metrics from our Trino cluster. Then we have our metric server of Kubelet and both for KEDA. These metric servers have inside their own system a set of event-driven based autoscaling triggers that if they get fired, the horizontal pod autoscaler would attach them, would fetch them and scale our cluster, whether scale up or scale down. So in the end, the Kubernetes event-driven autoscaling, which is KEDA, is just a wrapper around horizontal pod autoscaler that helps us to define more flexible and more event-driven and connect to, for example, connect to external resources to be able to scale smartly. I wanted to also discuss with you some of the triggers that we had in this KEDA setup. And the first one is the block driver per worker. Drivers in Trino terms just means the task executions. So in our setup, we had a scale up trigger. It would scale up when we have more than 100 block drivers, for example, and this shows workload situation in our system. The next one is running queries. So we will monitor the number of running queries, and if it passes a threshold, we will scale our cluster. Here for us, it says 0.2, and if it's a weird number for you, it's because we assume for each query we need 5 workers to run. So this way, this 0.2 comes into action. And this is just a preemptive scaling approach that we have. The next one, which is our reactive scaling approach, is queued queries. So we monitor our queued queries in our cluster, and if it's more than, for example, a threshold, we will just scale. It also helps us scale down to, and also one, because we don't want to scale down to 0, because we always want to be able to roll up our cluster fast enough. And these numbers, these thresholds are not like the final. Definitely try it out with different thresholds if your use case is different. But these were the numbers for now helping us. So now that our cluster autoscales, we could run a little bit like more advanced queries and more heavy queries. We wanted to also make sure that the performance of those queries are better than what we have in Athena. So what we came to play with is the worker node tags. So the workers are the set of the instances that are running the queries for us. So we first thought, okay, because maybe we have large and huge amount of data sets, they would be memory bound. So for that, what we did is to put the workers in the first phase on memory optimized instances by the AWS. Actually, it was not the case for us. We found out after this that our queries are more of CPU bound instead of memory bound. So what we did in phase 2, we switched to compute optimized instances and we immediately see some improvements, and the cost was kind of the same as what we have with memory optimized version. In the third phase, what we wanted to do is to cut some costs also. So we tried the ARM-based instances, which are the G-type, Graviton type of the AWS, and we saw the kind of the same performance, but the costs were so much lower. So this was a huge step for us. And in final phase, we added network optimization to all of these. Why we needed this? Because our workers are communicating with S3 a lot, and this communication is network bound, and we wanted to make sure that we have enough bandwidth for our worker to be able to connect to S3. So this was also a huge help for us to be able to run queries faster. So in the end, our final node pool strategy looked like this. The first two are running all on spot instances by AWS, which is cutting around 70% of costs for you, which is really nice. So first we go and see if there are compute optimized Graviton-based or compute optimized Graviton-based network optimized instances available on a spot. We then put the workers on these nodes. If not, on second try, we go and see if there are normal Intel-based compute optimized instances or the network optimized versions of those available on the spot. And then we put the workers there. And if none of those have available space for us, what we do always, we have the fallback on on-demand instances. And we don't want to make the queries being idle and the BIs waiting for workers to come up. So we always fall back on demand to make sure our cluster is up and running. So now our workers also on the correct path. What about data caching? Why data caching would help us? Because it would boost our performance, it would prevent network congestion, and it would save some costs. What data I mean here is the data of your data lake that comes each time from S3 to our workers. This was possible to set up via the Helm chart. You just need to enable a flag, choose a path to save your cache data, and choose the amount of percentage of the file system that you want to save the data inside. And this implementation is done thanks to the Alexio team in the Trino. So how it works is that the Hive connector comes and looks for the cache. If the cache hits, it goes and gets the cache data from the file system of the worker. If not, it would just go and continue as before and get the data from S3. Okay, now the performance is also kind of reliable. We can rely on our performance of system. It auto-scales in time. It can connect to the different buckets and data lakes. But we wanted to make sure our cluster also is resilient and it can operate on any conditions. So as you can see in this diagram, we have our coordinator, which was only one pod and on-demand instances. And why it's that? It's because coordinators are like hearts of our system. And if this coordinator goes away, all of our query progress and the query management would get lost. So we needed to make sure this heart of our system is always up and running. So we put them on-demand instances, and in the end, it's just one pod. It also has some fault-tolerant execution on top to make the coordinator more resilient. And this fault-tolerant execution would retry the queries if they fail automatically. But for workers, it's a little bit different. Why? Because imagine you have 500 workers. Imagine putting all of them on on-demand instances. Then the project manager would come again. This time would brag about Trino, and that's what we wanted to prevent in the first time. So this is not the solution. So we needed to put them on a spot instances. This will, again, help us save around 70% of money. But you needed one more step ahead to make sure these spot interruptions would be handled well. Because when Carpenter, which is our node controlling tool, comes and asks us for the pod, comes and asks for the node, because the node is an spot instance. This way, we need to make sure that, okay, we have a graceful shutdown flow set up to make sure that the whole process of taking the instance away is smooth and fluent. To make sure of that, we have the flow which looks like this. When the shutdown API comes and gets called, you have 2 minutes for AWS to finalize your work on the worker, because this is the amount of time that AWS gives you for each spot interruption. So we set the termination grace period seconds at 120 seconds, which is at 2 minutes. But for grace period seconds, we put one number for now, it's 30 seconds. And what's that grace period seconds? So when the shutdown API gets called, we sleep for 30 seconds, for example. That in that 30 seconds, a coordinator makes sure that it won't send the queries to the workers that is gonna go away because of the spot interruption. Then it will the worker will block all the active tasks until they are complete. Then we will sleep again more 30 seconds to make coordinator know that all the active tasks are finished. And then in the end, like 10-15 seconds, it takes time for Trino application to exit. So all this flow goes to make sure that the coordinator won't send the queries to the workers that are going away. One more thing that made our cluster more resilient is Exchange Manager, and we are using Exchange Manager with S3. And what that means is that, for example, imagine you're running a query, and this query is running on 10, 12, 15 workers. Then suddenly one of the workers gets interrupted because of the spot instances, and you need to retry the query. This is okay. This is already some kind of resilience because the query will get rerun. But imagine the poor BI waiting for this query to run for 30 minutes. And why? Because, for example, one spot interruption came and happened. So what Exchange Manager do for us here is that, so each query on Trino, when from the coordinator goes to the workers, splits to different spills. And these splits are like the intermediate steps of our query that gets calculated on each worker. Then in the end, all those calculations goes inside coordinator, gather, and shows us the result. So what this Exchange Manager does is that to save these intermediate steps on S3 for us. So if the spot interruption comes and gets your 15th, for example, worker, which is your final worker, the new worker comes and gets that intermediate data from S3, doesn't need to calculate everything, and this way your retry would take much less. None of these setup from the autoscaling to performance to resilience would be possible without monitoring. To make sure that we can monitor our cluster, we need to first expose some metrics. And to expose some metrics, you can just expose a JMX exporter in Trino, which is available as a site container, but there is a catch with it. So imagine you have 300 workers running at the same time, and all of them are exposing all the metrics Trino can expose. This will ruin your Prometheus instance and cluster. So you need to make sure here that you have a set of rules for your metrics to just expose the metrics that you need in your cluster. And for example, where we use them, for example, in our Grafana dashboard, we have, for example, dashboard to show number of queries. We have our execution time, P95 and P99s, and all of these dashboards helps us understand the performance of a cluster and shows us, okay, whatever change we make in our cluster, what effect it actually had in it. One more tool that we added here to make our users, which are like BIs, BizOps people's life easier, is Querybook. So they were used to use the AWS Athena console to run their queries and analysis. But we needed somehow a similar thing which Trino doesn't have by default, and Querybook was our answer. Querybook is an open source technology by Pinterest, and it has a really nice UI. You can log in, you can see all the databases and tables and run queries there. And even nicer thing is that you can do a lot of stuff with the results of the query. For example, you can share them with another BI. You can export them as CSV format in an S3 bucket. So it gives us a lot of options. So now let's talk about results and next steps. So we made the initial decision in May 2025. We then did our initial deployment in June. We had our initial rollout to BIs in July. We then had our improvement loop and feedback loop process in August. And from September, we started to roll out some production workloads, like, for example, some dashboards, some manual analysis, and also some DAGs. And what we plan until end of this year to migrate completely all our DAGs, pipelines, dashboards, manual work, everything from Athena to Trino. So we already see some improvements also in costs. If you see in this part of our cost diagram for Athena versus Trino, you can see around end of September and middle September, we had a spike in our Athena costs. And it was because one of our projects, one of our teams had a project release, and that was using Trino, was using Athena to run some calculations. And at the same time, we discovered this spike, discussed with them, and communicated with them to migrate all those Athena tasks to Trino. And you can see here that after the migration, the Athena costs decreased, but at the same time, the Trino costs didn't increase, which shows we already saved some costs. How we make sure these cost improvements continue? We are utilizing Spot. We now per compute, not terabytes of data scanned, and this brought us for now around 33% of cost decrease, which we hope to increase soon. We also have another project and another success story from our senior data engineer. They had a different project that they recently migrated from Athena and Trino, and that was a huge success for them and for us. Why? Because their calculations were running for 1 day before, and now with Trino and the way we fine-tuned our cluster for this part of the project, it made it just 1 hour. Thank you so much, everyone. This is some useful links that you can use, our engineering blog. You can scan our LinkedIn, and I'm here for your questions. Thank you.